experienced in their life, but you may not have really thought about the science behind it or how it works. And that's because today we are going to be talking about temperature and heat. So what is temperature? What is heat? How are they related? And as you know, physics is all about how things move. So the reason physicists are really interested in temperature and heat is because heat is constantly moving between different objects, different areas, different environments. And so some physicists spend a lot of time trying to figure out exactly how heat will flow between different areas. There we go. So today we're specifically going to be looking at how do we measure temperature, how the kind of general way that heat flows between different objects, and then specifically 3 different methods of heat transfer. So when we talked about electricity and electric charges, we talked about 3 ways that you can transfer an electric charge from one material to another. There are very similar ways that we can transfer heat. And so those we'll go over by the end of the notes for today. Hey, there we go. All right, temperature and heat. What exactly is happening in order to generate this heat, or in order to allow us to measure something like temperature? So to understand temperature and heat, you have to drill way, way down, super duper teeny tiny, down to the particle level. So temperature is all dependent on how the particles of a substance are moving. You may remember when we went over the electric charges, we talked about how you have your atoms, which are like your building blocks of the universe. And then the atoms are made up of the positive protons and the negative electrons, and that's where charge comes from. Temperature comes from when these atoms are moving. So all matter in the universe is made up of atoms, and all of these atoms are moving. Now, I might think, well, yeah, that makes sense for like water or air that's constantly sloshing around and moving around. But what about like this pen right here? It's pretty solid. How could the atoms in here be moving? There's nothing moving in this pen. Actually, there is. It's just happening down on a super duper microscopic levels. So even solid objects, the atoms are vibrating like a little tiny bit. Not enough for us to see, and not enough to cause there to be any sort of change in the material, but they're still moving. They're sitting in there and vibrating around a teeny tiny bit. So the fact that these atoms are moving a little bit means that the object has energy. So this motion from these atoms, these little bit of movement, gives the object energy. So the formal kind of scientific phrasing for talking about everything being made up of little atoms that are moving is called the kinetic theory of matter. Sometimes it's called the kinetic molecular theory, or the KMT, or the KTM. Whatever the kinetic theory is, it says that all the particles that make up matter are constantly in motion. So kinetic is just a fancy scientific term for like moving and motion. So the kinetic theory says all of these tiny little atomic particles are moving all the time. Now, what state that you're in depends on how much movement that the atoms show. So on Earth, we have 3 main states of solids, liquids, and gases. And then out in space, there's a 4th type of state called plasma. We're not going to get into exactly what makes up a solid, a liquid, or a gas. If you ever have taken IPC here, or if you take IPC in the future here with me, we'll talk all about them. The basic things to know for heat and temperature is that when you're a solid, the atoms are all just kind of vibrating around a little bit, but there's almost no actual movement of the atoms. So for the most part, they're just kind of staying in place right next to each other and just kind of vibrating in place. So they're just kind of shaking in place. If something becomes a liquid, liquids are a lot more fluid, right? There's a lot more flowy motion going on in liquids. I can swirl my water bottle here around and all the water inside sloshes back and forth. So in a liquid, the atoms are flowing a little bit more. They're not so much stuck in place, and they can kind of move around each other pretty well. They can't like zoom all over the inside of my cup, right? They're pretty limited in how much they can move, but they can still move around each other. They can flow around, so they have a little bit more motion, a little bit more energy. Gases have a lot more motion and a lot more energy, so their particles are able to move really freely around. They don't have to stay stuck close to each other like solids or liquids. There's gases in your room or in your car around you right now that are constantly zooming around over your head. They're just little tiny particles, so you can't see them. But they're going really fast. They're totally separated out from each other. And then plasma is at like the super top level of energy. In this case, the particles are moving so fast and freely that sometimes they come apart a little bit and go back together. So this is kind of the order of how fast and how much energy the different states of matter have. From the least amount of movement and sort of the slowest or lowest energy of the solids, increasing in motion and energy up to plasma. So on our little diagram over here, the further you get to the right in terms of your state, the faster and more movement and higher energy your matter has. And that's just what the kinetic theory says, is that all particles are in motion, but how much motion depends on if they're a solid, a liquid, a gas, or a plasma. So how is this related to temperature? How can we actually measure how much energy is in a substance? So temperature is that measurement. To us, on like our normal everyday kind of usage, it tells us about how hot or how cold it is outside, right? Every morning I have one of those Alexa smart speakers from Amazon, and pretty much every morning before I go outside on a walk, I go, Alexa, what's the weather? And she'll tell me the cloudiness, and she'll also mention the temperature. And so if it's 70, 80 degrees, I'm like, oh, nice. If it's 40, 50 degrees, I'm like, oh, that's too cold. So, but what temperature actually is the measurement of the average kinetic energy of all the particles in the object. Meaning the temperature is basically measuring how much energy or how quickly the particles in a specific object are measuring. So the more movement that you get, the more the particles are able to move around, and the quicker that they're moving, the higher your temperature. So how big the atoms in your matter are and how quickly they're moving determine the temperature of the object. So as matter gets more and more energy, as particles move faster and faster and faster, and when they do that, the temperature of the object goes up. So the higher the temperature, the higher the more movement of our particles. So for example, if we have two chocolatey drinks here, right? We have some, I don't know, let's say I said some chocolate milk fresh out the fridge and some hot cocoa. The chocolate milk is pretty cool, and so the particles in it are not moving very fast. They're low temperature particles, which means they have low average kinetic energy. They're moving kind of slow and sluggish. They're really not moving fast. When we pull that hot chocolate off the stove and put it into our cup, it's been heating up, which means that the particles have been moving faster and faster and faster and faster. So high temperature particles have higher average kinetic energy. The faster that your particles move, the hotter that your object is. All right, so as we go from a cold object to a hot object, we do that by speeding up the particles. We give them more energy, and the energy makes them move faster. So like when you're heating something up on the stove, you've got the heating element underneath it, right? Whether that's a natural gas like fire or an electric heater. But that energy is going into the sauce or milk or whatever it is that you're heating up and is being transferred to these particles in order to make them move faster and faster. So low temperature means the particles are moving slow. High temperature means that the particles are moving fast. So we measure temperature in degrees, right? And there's three kind of major scales that we use for degrees. So we have Celsius, which is used by most of Europe and Asia. We have Fahrenheit, that's mainly used by the US. And there's another scale called Kelvin that's used a lot by scientists. We're really not going to go too deeply into Kelvin right now, so don't worry about it. So temperature, the scales work a little bit differently. So in Fahrenheit, like we usually use, water freezes at 32 degrees and boils at 212 degrees Fahrenheit, right? If you stuck a thermometer into a puddle of water as it froze over the wintertime in somewhere that got cold enough for water to freeze, it would measure 32 degrees. If you stuck your thermometer in a boiling pot of water, it's going to measure 212 degrees Fahrenheit. There's also the Celsius scale, which scientists like to use because it's a little bit easier when it comes to water. And Celsius, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. So a little bit easier, 0 to 100 kind of range there. But they're both measuring the same thing. They're both measuring the amount of energy, the amount of particle movement in a substance, whether that's something on the stove or something in the fridge or just the air temperature around you. That is what your thermometer is measuring. That is what temperature is telling us. So the way that a thermometer actually works, you've all seen thermometers like this one, where you have some sort of liquid inside, and then the liquid goes up and down depending on if it's hotter or colder. And it's usually like a red or a blue color, so you can see it easily. So what's actually happening inside of a thermometer is that the liquid that is in there either expands, increases, or contracts and gets smaller by a certain amount due to a change in temperature. So changing the temperature of the liquid inside that little vial in the middle of the thermometer causes the liquid to expand out or contract down. It can actually change the volume of the liquid. And so when they're making thermometers, scientists will measure, okay, we know that we raised the temperature of this room by exactly 10 degrees, and the liquid went from here to here. So therefore, that must be a 10-degree difference on our thermometer. So when those particles move faster and faster, it can cause things like liquids or solids to expand or contract. And we call that thermal expansion. So all gases, all liquids, and most solids expand when the temperature increases and contract when the temperature decreases. So that's why if you've ever been driving somewhere and you're going across a bridge, I don't know if you guys have ever noticed, but I've always noticed that you go under the bridge and then you get this constant like ka-dum, 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 ka-dum as your car is going over. That's because the material of the bridge, made out of concrete and asphalt and stuff, will expand a tiny bit when it's summertime and it's hot, and contract a tiny bit in wintertime and when it's cold. And so people who first started building bridges out of the material noticed that they were constantly getting cracks and breaks in the bridge, because as this material expands and contracts, that can cause it to break over time. So they put these little joints in between, and it's essentially a little built-in break in the middle of the bridge. That means that when part of the bridge expands or contracts, it has like some room to breathe, essentially. Right? It's not completely sandwiched in by all the concrete and stuff around it. Each concrete segment has a little tiny bit of space where it can get bigger and smaller and not crack or break the other concrete segments around it. So again, when the temperature goes up, that means that those particle motion is getting faster and the particles are moving more and more. And so when that happens, that can cause the particles to get further apart from one another. Even in something like a solid, the particles can get a teeny bit more spread out than they used to be. And that can cause the material to expand or get bigger, take up more space. If you try to do this in a big chunk of solid material, you could end up with something cracking or breaking, which is not good. That's not something that you want to see in your bridge, is big cracks forming after a couple summers and winters go by. All right, so we've got our particles in our matter. Temperature is how quickly those particles are moving, with a higher temperature meaning faster motion, and a lower temperature meaning less motion, lower amounts of motion. And that change in motion is what allows us to measure things using thermometers, because it causes the material to expand or contract a tiny bit. And it is what causes us to have to put in these breaks in things like bridges and roadways, in order so that the materials have a little bit of room to move. All right, any questions about temperature or particle motion or anything like that so far? All right, I'm not hearing any. So we'll move on from there to talk a little bit about energy, temperature energy, which is in the form of heat. So heat, what we call heat, isn't necessarily something that has a high temperature. In physics, heat is the flow of energy from an object at a higher temperature to an object at a lower temperature. So when two things are next to each other and one of them is hotter and one of them is cooler, energy will naturally flow from the hotter object to the cooler object. And we call this energy heat. So in order for there to be heat in a system, there has to be some sort of energy movement. Now, in addition to temperature, which is the average motion, the average kinetic energy of particles in a substance, There can also be thermal energy, which is like the total amount of kinetic energy. If we took all of the particles in our substance and found out how much energy they have and put that all together, we could know the thermal energy of that substance. So we're not really going to talk a lot about thermal energy today. We're mostly going to focus on heat, how we can get energy to flow from warmer to cooler objects. So heat, there's a couple different ways that we can measure heat. It's traditionally measured in something called joules. So joule being a certain amount of heat, certain amount of energy being transferred. We can also measure heat in something called calories. So you've probably heard of calories before. These are what we use for energy in our body. That's how we measure how much energy our body needs or how much energy that a piece of food will give us. And scientifically, a calorie is related to that, but specifically, one single calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degrees Celsius. So if we want to get 1 gram of water, which is a pretty small amount of water, if we want it to go up in temperature by 1 degree Celsius, we would have to add 1 calorie of heat to that gram of water. And a calorie is equivalent to about 4.18 joules. So about 4 joules will raise 1 gram of water 1 degree Celsius. So again, we're adding energy into a substance, in this case water. And when we do that, it causes the temperature to go up. So that's what heat is. Heat is the energy that's added to something that will increase its temperature, or the energy that's taken away from something to lower its temperature. It can go in the opposite direction as well. So across the natural world, there's a whole bunch of different types of matter out there, and some of them change their temperature a lot more easily than other ones do. So the specific heat of an object is the amount of energy required to raise 1 gram of that object by 1 degrees Celsius. Like we already said for water, which is at the top of our little table here, it takes 1 calorie of heat in order to raise that by a gram per degree Celsius. So water, actually, that is a pretty high specific heat. I don't know, I'm assuming a lot of you have boiled water on the stove before. And even over a stove that is cranked all the way up to 10 or all the way up to high and is really blasting out the heat, it takes a while for water to come up to a boil, right? Depending on how much water you have in there, it could be 7-8 minutes before it starts boiling. So the specific heat of water is actually pretty high compared to other stuff. So it takes a relative large amount of energy in order to heat up water. A lot of other kind of everyday substances do not have this issue. They can heat up and cool down pretty quickly. So things like aluminum, right? So like the metal can, like a metal Coke can or something. I don't know if you've ever like washed those out in the sink where like you fill up the inside with water for a couple seconds and then dump it out. If you're holding onto that Coke can with your bare hand and the sink is really hot, then as soon as that can starts to fill up with hot water, you can feel the heat on your fingertips, right? So it does not take very much energy in order to increase the temperature of aluminum by 1 degree Celsius. Same thing with things like concrete or asphalt. All right, if you've ever been walking around outside on a summer day and you had bare feet on and you're going to go walk in the street, you're going to learn that in Texas, that is a bad idea. And you're going to learn that pretty quickly because things like asphalt and granite heat up really, really quickly when they are introduced to energy. So it does not take very much. It takes 0.2 calories of heat in order to raise asphalt by 1 degree Celsius, 1 gram of asphalt by 1 degree Celsius. So the higher the specific heat you have, the more energy it's going to take in order to heat up that substance. With water being a kind of everyday substance that has a surprisingly high specific heat. It takes a lot of energy to heat up water compared to a lot of other stuff that we deal with on kind of our day-to-day basis. So how exactly can we transfer heat? How do we get the heat from our hot object to our cooler object? So there are 3 ways that we can do this. And some of them might sound a little bit familiar from when we talked about moving charges around last week. So we have conduction, which is very similar to the one we already talked about with our charges. We have convection, and we have radiation. So each one of these 3 ways moves heat from one area to another. So I'll come back to this picture at the end after we kind of talk about them. But essentially, conduction is heat moving by direct contact with something hot. Convection is heat moving through a big fluid like air or water. And radiation is the heat that naturally radiates out from a heat source. So, first one that we're going to talk about is conduction. You may remember when we talked about electric charges, I mentioned that conduction happens when you take a charged object and you touch it to an uncharged object and the electrons flow. Very similar thing happens with heat. So when one object passes heat to another, because they are directly touching, they are touching physically with each other, that is called conduction. So just like in electricity, where we had conductors like metal that move things very easily, and insulators like rubber or plastic, which did not, same exact ideas apply to heat as well. Conductors are materials that transfer heat and energy easily. Same types of materials, things like metal. And insulators do not transfer energy easily, things like rubber and plastic. So that's why the bottom of your frying pan is made out of metal, but the handle of it is made out of some type of plastic or silicone. Or that's why the dishes that you put in the oven are made out of metal, but your oven mitts are made out of that thick wool material, because wool is a good insulator and it will not transfer the heat from your metal baking tray to your fingers. So for example, you're holding on to a hot cup of cocoa and your hands are warming up. So the water inside the cup is hot, right? You heat it up on the stove, you mixed in the little Swiss Miss chocolate powder, and then you poured it into the cup. So the water is hot. The water is touching your cup. So the cup is getting hot. And then your hands are cold and they're touching the cup. So your hands are heating up because there's heat passing from the cup to your hands because they are directly touching. So it's kind of like with this metal rod right here. The metal rod, imagine that it's sticking directly into the fire, like it's touching one of the logs of the fire. And then the heat travels up the rod and into this person's hand. Luckily, they're wearing a glove, so it goes from the rod to the glove, which does not let it go through to the fingers. But if this person was not wearing a glove, they'd be in for a bad time because they're physically touching the metal rod. The metal rod is hot, and so it's naturally going to move heat from the rod into your hand. If there's too much heat, you're going to get burned. So things that are good conductors, again, transfers heat very well. Things like metal, things like wire. Water can be a good conductor. All right, once you get water heated up, then anything that touches it is going to get hot as well. And then you also have insulators, things like foam or rubber or wood or paper or even like wool, like thick fabrics are good insulators. They do not transfer heat very well. All right, so conduction, you have to be physically touching an object for the heat to move. You can also have convection, which is when you get a lot of particles all moving in kind of the same circular direction within some sort of fluid, whether that fluid is a liquid like water or a gas like the air in a room. So in convection, you're moving the particles around, and that is kind of carrying the heat throughout the system. So like, for example, with our boiling water right here, the water at the bottom of the pan is being heated up by conduction because the pan is being heated by this flame right here. And the water right down here is directly touching the bottom of the pan. So it's being heated up by conduction. But what about the water at the top? The water of the top isn't directly touching a heat source. It's just kind of sitting there. But eventually that water is going to get hot too. And that's because thanks to convection, as the water at the bottom gets heated up, it'll move up to the top of the pan. So as things get heated up, as things expand, they tend to float to the top of their system. So as the water down here gets heated up, it naturally rises to the top of the pan, and the water at the top, since it's cooler, will naturally fall down to the bottom. And it creates this cycle where the water gets warmed and then it comes up and it cools down, then it goes back and it gets warmed until all the water is heated up till the boiling point. So the convection is essentially heat being moved through things like air or water, through this kind of process. Same thing happens with like a radiator or a heater in a room of your house, right? So even though the radiator is turned on over like on the side over in the corner, eventually the whole room will start to feel warm. And that's because the air right around the radiator that is touching the radiator and absorbing that heat, as it gets warmer, air rises, and then cool air comes in to take its place. So the warm air goes up, the cool air comes down, and eventually the cool air will be warmed and go up, and it creates this cycle to where eventually warm air will spread throughout the entire room. So we see this convection process happen a lot on like really big scales in nature, where cooler and denser air will sink kind of underneath the warmer air, which is rising up. And then once the warm air gets really high in the atmosphere, where it gets really cold, it starts to cool down again. And so then we'll fall back down, whereas the warm air down near the surface of the Earth will start rising again, and it creates this convection cycle where you get cool air and warm air kind of circulating throughout the atmosphere. So convection is all about these kind of circulating fluids of heat, whether that's in a pot of water or in a single room or in a really big scale, like in the atmosphere across the entire surface of the Earth and even underneath the Earth's surface. So in the mantle, where you have the lava layer underneath the crust of the Earth, you have the same thing happening where the lava closer to the core, to the middle of the Earth, is hotter, so it'll naturally rise up to the top, and then the cooler lava will fall down and create kind of this cycle of heat being distributed throughout the core or throughout the mantle. So all of these are ways to move heat into cooler areas. In convection, it just happens on this kind of cycle pattern. So the same thing is happening with our fire example from earlier. So as the air that's right around the fire heats up, it'll naturally rise up. So as part of what the smoke is the hot air rising. So if you stick your hands in that, you can feel all that hot air coming off the top of the fire, right? Because the air is being heated up, and when air gets heated up, it rises. So that's what we call convection. There's also things called convection ovens, which normally an oven, you just heat up the inside and it gets hot and that's what cooks the food. But a convection oven also has a little fan in there that keeps the hot air moving. And so by constantly making sure that there's hot air moving across the surface of the food, that helps to cook things a little bit quicker. Usually you'll see it in things like smaller ovens, like kind of like toaster ovens, or the air fryers. Like those are really, really popular right now. Those are basically small convection ovens. So they fry the food by moving very hot air very quickly across it. So the food is not just getting cooked from the heat of the oven warming up, but it's also being cooked by the hot air that's being pushed across it by this little fan. So then finally, our third main type of heat movement, and probably one of the most common ones that you deal with on a regular basis without really realizing it, is called radiation. No, this is not like the super dangerous radiation that comes out of nuclear power plants and stuff like that. This is natural radiation given off by heat sources. So radiation is the transfer of energy by what are called electromagnetic waves. So we are going to talk about EM waves, electromagnetic waves, on Thursday. Actually, we'll go over kind of basics of what they are. But essentially, these are types of waves that move through the world, move through the universe, and transfer energy. So like the light that you can see right now, that is a type of wave. The microwaves that cook things in your little microwave oven, those are EM waves. Things like infrared light, like if you ever see like the heat scan of something, or ultraviolet light that you have to put sunscreen on for. All of those are examples of radiation. So partially as a result of this radiation, heat can move by radiation as well. So when this radiation energy is emitted from one object and then is absorbed by another, usually that will result in transferring heat. So if a warmer object is giving off the radiation and the cooler object is absorbing it, that is resulting in a heat transfer. So for example, for most ovens, like your big standard oven, that you have in your kitchen. You turn on the oven, set it to a certain temperature, and then either the gas burners or the electric burners in there will heat on and start warming up. There's not really a lot of air movement since it's one kind of enclosed space, so you don't really have convection. But because those gas burner or electric burners on the bottom are getting hot, they're radiating heat to the rest of the inside of the oven. And so even though air might not be directly carrying the heat all around, and the air that's like at the top of the oven isn't directly touching the heat source underneath, the radiation from this electric or gas heating element is enough to heat up the inside of your oven. It's the same reason why when you sit next to a fire, you can get the warmth from the fire. So if you held your hand over the top of it and you felt like the hot air rising from the fire, that's conduction. But if you're sitting next to the fire, you put your hands out and you can feel the heat coming off of the fire. That is radiation heat. That heat is being radiated out from the fire. It's transferring heat across space. So you don't have to be directly touching the fire, and you don't have to be feeling the hot air coming off the top of the fire in order to get some of that warmth. The same thing happens on a really big scale with our sun, right? The sun is the reason why the temperature is what it is during the day. During the summertime in the United States, we're pointed closer to the sun, and so we get more of the sun's radiation, which gets the temperature warmer. In the wintertime, we're pointed away from the sun, so we get less radiation, so we're cooler. But this is why if you go from like a shaded area to a sunny area, especially in the summertime, you feel warmer. You can feel the heat from the sun on your skin. The sun is millions and millions of miles away, right? Even moving at the speed of light, it takes 8 minutes from the light from the sun to reach your eyeballs here on Earth. But we still get the warmth from the sun. The sun is so incredibly hot and so incredibly huge that it produces tons of heat. And that heat is able to travel across those millions of miles of space, land on the Earth, and heat us up to, today, a particularly nice 73, 74 degrees Fahrenheit. So that's why when you're in the sun, you feel warm. And when you're in the sun for too long, you can get a sunburn. If you absorb too much of the sun's radiation, it can actually burn your skin. Again, the heat isn't getting to you because it's being carried in the air from the sun. There's no air in space. Radiation, the cool thing about it is that it can travel through empty space. So a lot of times in order for energy to get transferred, it has to move through some sort of substance. So like sound, for example, is a type of energy. So sound has to travel through air. It travels by vibrating air particles, which vibrate the next air particles, and so on and so on. So if you're in space and someone screams at you, you can't hear them because there is no air to carry that sound in space. For radiation and heat, that doesn't matter. It can travel through empty space and make it all the way to Earth and warm us up here on Earth. So that's why on our fire picture from earlier, even by holding your hands close to the fire, but not directly in the hot air, you can still feel the heat because there's heat radiation coming off of the fire that is warming up your hands. So radiation, heat, doesn't require you to be directly touching it. It doesn't require like air or water to carry it. It just naturally moves from a hotter to a cooler area. So people have done really cool things with this where they use the sun's radiation in order to cook things. So normally when you want to cook something, you put it into the oven, turn it on, and the radiation from the heating element in the oven will cook your food over time. Some people have developed ways to capture enough radiation from the sun's rays in order to cook food as well. They're called solar cookers, and it basically uses things like mirrors and foil to capture and concentrate a whole bunch of the sun's rays into one area. That area specifically being the food that they want to cook. So it's nice because it doesn't require any energy, it doesn't require any electricity. You're using something that's already naturally being produced from our sun. And you're capturing all of that heat energy and focusing it into a kind of concentrated area. So we have our conduction transfer of heat where we're transferring by direct contact. Things have to be touching in order for the heat to go from one area to another. Again, energy is always going to flow directly from the warmer object to the cooler object. Convection is when you get that cycling inside of a fluid, like a gas or a liquid. So you have a large number of particles that heat up and then move in kind of the same direction and create that cycle. So as long as there's kind of a warm area and a cool area of your system, you're going to get this convection occurring as things heat up and then move and then cool down and then fall and then heat up again and then rise and then cool down, so on and so forth. And then finally, you have radiation or energy transferred by those EM waves, energy that is transferred across space, not directly by touching or moving large particles. So we get radiation from the sun because that heat and that energy from the sun can travel through the empty space and come here and land on Earth. All right, you can feel the radiation from a fire, even if you're not touching it, because of this radiation traveling from the fire through the air to your hands. So these are the different ways that we can move heat from one area to another. And as long as there's differences in temperature, that heat is naturally going to flow from the hot area to the cool area. All right, so that is temperature and heat. Temperature is sort of the measurement of how quickly the particles in a matter are moving, with faster particles meaning that you have a higher temperature. And heat is how we move that energy from one set of particles to another. How we flow from the hotter objects to the cooler object. So that's why when you put your food in an oven, it gets cooked, because even though if you have a perfect oven, the entire oven is going to be exactly 350 degrees wherever you go. But you put the food in there and the food has been prepared by you and maybe it's only 70 or 80 degrees. So the energy from the heat is naturally going to flow from the 350 degrees in the oven into the cooler food. It's trying to essentially bring the food up to the same temperature as the oven. All right. Any questions about heat or the different ways that heat is transferred? All right, so that was the basic things that I wanted to go over you about temperature and heat. Just sort of really hit on the basics to talk about what exactly are temperature and heat and how does heat work in terms of transferring from one area to another. So the homework for tonight should be, at least in my opinion, it's a pretty short and sweet and to the point one. There's a question about that kinetic molecular theory. I want you to rank the different states of matter from 1 to 4, where 1 is the slowest and least movement, least energy matter, and 4 is the highest and most quickly moving state of matter. The next part down here, I have some different areas. The living room at 78 degrees, the outside at 94 degrees, so this is a pretty average day here in a couple months, and the attic, which is 120 degrees. So I want you to tell me, using these little arrows right here, which direction is the heat going to flow in these situations? Like for this first one, is it going to flow, in this case, to the left from the air to the room, or is it going to flow to the right from the room to the air? And so for each one of these, I want you to tell me which way will the heat flow, from the left to the right object or from the right to the left object. And then finally, the last set of questions down here, I lay out a couple of different scenarios for you. And I just want you to tell me, is this an example of conduction? Is it an example of convection or of radiation? So burning your hand on a skillet, feeling the warmth from the sun, circulating hot air in an oven, warming up with a hot cup of coffee, toasting marshmallows next to the fire. I want you to tell me, for each one of these, what type of heat transfer is in that following situation. So pretty simple. And then on Wednesday, we're going to have our final writing assignment for the term. Again, please make sure that you write your full name and, oh, I got to switch this to 5 points. Full name and the date on the top of it. This is just kind of a very general question. It has nothing to do with like heat or temperature. But I just want you to write about, what did you like learning in physics this term? So like, what was your favorite part of the class that we went over? And what did you dislike learning about? So what was the thing that you got that you never really fully understood, or it was just really hard for you to understand? So what did you think was boring or hard to wrap your head around? So again, final handwriting assignment. You guys have all turned these in so far, so you know what you're doing. But again, full name and the date at the top, handwritten down on a piece of paper. Then take a picture and either add it to the Google Classroom, text it to me, or email it to me. All right, so that should be everything that you need to know about before we have our last class of the term together next, or not next Thursday, but this coming Thursday. So does anybody have any final questions about the worksheet for homework tonight or the writing assignment for tomorrow?
No, I don't think so.
All right, awesome.